Good evening, everyone. Welcome to the October presentation of an evening at Skidaway. Thank you so much for joining us. As always, if you would like to ask questions, you can use the chat function in YouTube. You can ask your questions at any time. However, our moderator, Dr. Dan Onimus, is going to kind of collect them and read them back at the end of the program. So you can ask questions anytime. We're not going to field them until the end. I'd like to introduce our speaker tonight, Dr. Clark Alexander. Dr. Alexander is also the director of the University of Georgia Skidaway Institute of Oceanography. He's a geologist by specialty. He received his bachelor's degree, 2 bachelor's degrees from Humboldt State University in California, and then both a master's and a PhD from North Carolina State University. He joined the Skidaway Institute in 1989 as a postdoctoral fellow and was appointed director in 2017. And so, without further ado, Dr. Alexander, take it away.
Thank you, Mike. So tonight, as you can tell from the title here, we're going to be talking about earthquakes and tsunamis. What I'd like to do is we're going to start out with a discussion of global features in terms of how they impact the distribution of earthquakes. We'll do a quick primer on plate tectonics for those in the audience that aren't as familiar. We'll talk a little bit about local and regional seismicity, and then we will bring this all around to talk about tsunamis, which are typically earthquake-created ocean-based features that we also at least need to be thinking about as residents along the coast of Georgia. But first, what I want to do is, I think I really missed an opportunity when I was choosing the title for my talk, because I wasn't aware that the 25th James Bond movie was coming up. So I want to change the title of my talk to Shaken, Not Stirred, Earthquakes and Tsunamis with the suave James Bond. And with that brief levity, I'd like to move on with the talk. So when we look at a global view of the Earth, here's a view. This is elevation and depth. The darker the blue, we're looking at deeper water. The redder something is, the higher it is in elevation. And the first thing that we can see is that we've got several large ocean basins: the Pacific Ocean Basin, the Atlantic Ocean Basin, Indian Ocean over here, which have very deep depths in some areas where the blues are very, very deep. There are areas that are less blue, indicating that they must be a little bit higher, not quite as deep. And then on the continents, we see that there's a broad diversity of elevations as well, both areas that are very high, like the Andes mountain range down here in South America, the Western Cordillera of the United States, the Himalayas in India and in this portion of the U.S., and then in the U.S. and in Asia, and then areas like Greenland, which also sit very high. So there's a great diversity in elevation and depth around the world. And actually what these elevations are telling us, they're giving us hints about how the surface of the Earth is divided up and how it's working. If you're familiar with plate tectonics, you'll know that these areas that are a little bit higher in elevation in the middle of the ocean basins represent spreading centers. Those are areas where the oceanic crust is being created. It's warmer. It sits a little bit higher off the bottom. And so those form one boundary of our plates. And then we have areas where plates are being brought together. And those are where we traditionally and typically see these high elevations. Now, if we look at the distribution of these plates on the surface of the Earth, we see that out here in the Pacific, we have one big plate with a spreading center that's on the eastern side of the Pacific Ocean, which actually comes up into the continent in the US here as the San Andreas Fault up in the Gulf of California. We have areas where plates are coming together. These arrows show the direction of plate movement. So when you have arrows that are pointing towards each other, such as here on the South American plate and the Nazca plate, these are areas where the plates are coming together, and something has to be happening where they're coming together. Either you must have one plate being driven underneath the other plate, just as the Nazca plate is being driven underneath the South American plate. And in areas like this, where you've got what's called subduction, these are areas where we have earthquakes forming. These are areas where we have large volcanic centers. These are areas where we have large mountain ranges, because all of this compression is driving up the one plate over the other. In contrast, where we have in the middle of the ocean basins what are called spreading centers, these are areas where new crust is being formed. The plates are moving away from each other. Here you can see the North American plate is moving in this direction. The African plate is moving in this direction, and the Eurasian plate is moving in this direction. So we have plates moving apart, and we don't have areas where you've got active compression and plates being driven together and all kinds of active tectonics. Similarly, here along the Aleutian chain, along the Japanese islands, and through the Pacific and South, Western Pacific and South Pacific, we see that we have subduction zones. These are areas where the Pacific plate here is being driven under different plates. The Philippine plate here, Eurasian plate here, Australian plate here, and you can see that we've got convergence again, arrows pointing towards each other in areas where we have a lot of compression and subduction. So if we look at the distribution of earthquakes, now this is just the last 20 years of earthquakes that I'm showing you here. And you can see that in general, where we see earthquakes are all along these convergent or these compressional boundaries that I was talking about just a moment ago. Here along South America, West Coast, here along the US, West Coast, up along the Aleutian Island chains, here all through the Northeast Asia, down through Southeast Asia into the South Pacific. And so where we have compression, we see that we are getting more and frankly larger earthquakes. We do see that there are a few earthquakes located along the spreading centers, but these are widely spaced, they're infrequent, and they're relatively small. One of the cool things for those of you that have been to Iceland, that's one of the latest places to go on my bucket list, is that the spreading center goes right through the middle of the island of Iceland. And so you can actually put one foot on one side of on the North American plate and one side on the Eurasian plate and actually be standing on two tectonic plates at once, which is cool if you're a geologist, I guess. So that's just the last 20 years of earthquakes. The other thing I want to point out here is that these earthquake magnitudes are colored by depth. And so they go from this pinkish color, which is close to the surface, down to the green color, which is a little bit deeper, maybe 70 kilometers depth, to the yellow color, which is somewhere between 70 and 300 kilometers deep into the interior of the earth, down to these red colors, which are somewhat deeper than 500 kilometers down. So you can actually see the downgoing plate and see it having earthquakes on the surface where the overriding plate and the downgoing plate are interacting with each other. And those interaction points get deeper and deeper because that plate is driving down into the mantle. So earthquakes get deeper as you move inland, and also as those interactions occur, we also get volcanoes occurring because you're melting a lot of that material that's been taken down. So not only are these areas that have a lot of earthquakes, there are also areas that have a lot of volcanoes in general. And we see that here in Northern California up through Oregon and Washington. We certainly see it through the Aleutian Island chain and all throughout what's termed the Pacific Ring of Fire because of the presence of these volcanoes throughout the area. If we look at the location of basically all the significant earthquakes, and the definition of significant just means that there was either a death, it was over $1 million worth of damage, which is actually pretty trivial in today's world, that it did significant structural damage. Those are the major components of what a significant earthquake is. But you can see that all the significant quakes, by and large, to a great degree, are all clustered along these convergent zones, the active margins that we were talking about. And you don't see any really along this raised mid-ocean ridge that we were also discussing earlier, here nor in the Atlantic. You have a few, but they're very, very few and far between. So we have a lot of convergence in the Pacific, and in the Atlantic, we really don't. We have plates that are moving away from each other. Now in the Caribbean, of course, you do have convergence and volcanism going on, but that is not related to the spreading of the Atlantic Ocean. So if we put that all together, we can, folks have put together seismic hazard maps for the world, and you can see that there's high seismic hazard, earthquake hazard, all along Alaska, down through the US West Coast, down along Central America, all throughout South America, where the convergent plates are. You have similar seismic hazards here, where there's a spreading rift beginning to form in Africa. There's also a large scale group of faults that are convergent areas up through Turkey, around the northern Mediterranean, and then into where the collision between the Indian continent and the Asian continent has occurred. Excuse me. And then, of course, all through the Pacific Ring of Fire, as we discussed a little bit earlier. So globally, seismic hazards map to areas of high tectonic activity. And when we look at the US, if we zoom in a little bit now to become a little bit more focused, if we look at topography here and the tectonic setting of the US, as we've mentioned, it's pretty obvious to see that the west coast of the US is much more tectonically active. We have the spreading center coming up here from the East Pacific Ocean. The spreading center goes up through the middle of the Gulf of Mexico, comes ashore as the San Andreas Fault here in very southern California, goes up along the California coast, goes out to sea near San Francisco, just north of San Francisco, and then goes back out to sea at Cape Mendocino here. And there's a little piece of the plate called the Farallon plate, a different plate that's still being subducted under the northern US and Canada on the west coast. So this is a very active tectonic setting, and we'd expect there to be high seismic activity and seismic hazard here. Now, if we look at the Atlantic basin, here we can just see on the far right of the slide, just a little bit of the spreading center that you can see here, that little jagged yellow line. We've got these little offsetting faults called transform faults that accommodate differential rates of spreading, and that's what these black lines are. And so you can trace those transform faults that show the opening of the Atlantic basin with the basin getting larger and larger, and the North American plate moving west, and the Eurasian plate and the African plate moving east. So we don't really see a lot of things that would make us expect that there would be a high tectonic vulnerability here. You know, the best we can do is this little weeny mountain range here that is so old and eroded that, you know, it just barely sticks up in comparison to the West Coast. But when we look at the US seismic hazards map, we do see what we expect on the West Coast because of the tectonic setting. We see high seismic hazard associated with Yellowstone and the Yellowstone caldera, which is in the past was a very large volcanic system, which there's still research going on to find out how active it is now. But when we look at the eastern half of the US, we actually see that there are some zones where there are high seismic hazards that you wouldn't really guess over time. Now, this zone of seismic hazard is related to the opening of the Gulf of Mexico. Whenever you have an ocean basin starting to form, you have three branches. You have, it's kind of like, well, let's see, kind of like that. And only two of them end up connecting up and spreading apart to form the ocean basin. And the third one gets abandoned, and that's termed an allocogen. And that is what we have that runs up through the center of the US and just so happens to be where the Mississippi River flows. And all that sediment is flowing down in this area that was weakened while the Gulf of Mexico was opening up as a new ocean basin. And so it's a structurally weak area that had a lot of sediment loading on it. And there were actually three large earthquakes in the winter of 1811 the early winter, November through January 1811 to 1812. They had three 7.5 to 8.0 Richter scale earthquakes in what's termed the New Madrid seismic zone. And there's been a lot of work done to try to figure out what the recurrence interval on those earthquakes are. I'm not familiar with what they are, but during those earthquakes, the effects of them were felt all the way up here in Maine. They were ringing bells in Boston in church towers. It was that strong of several different quakes. And the reason that it really isn't high in people's minds is that there just weren't many people around back in 1811 in this part of the country. So there wasn't a lot of damage, although locally it was important. The other area I want to point out is right here. You know, we're right down here in Savannah, and there's another area of high seismic hazard here related to the 1886 Charleston earthquake, which was about a 7.5. And we'll talk a little bit more about that when we talk about local examples. But there are areas, and the reason we don't really see them is that the fault systems and the expressions are deeply buried under a lot of sediment here, whereas on the West Coast, most of the seismic activity is very visible because there isn't a lot of sediment that's been shed over millions and millions and millions of years, burying those traces that we'll talk about in a moment. So one thing I want you to take away from, earthquakes are happening all the time. So this is the last 6 months here in our region. And you can see during the last 6 months, there's been a couple earthquakes in Georgia. There's been a couple down here near Charleston, you know, in an area that we're familiar with. There's been a string of earthquakes all along, which appear to be structural features here in the New Madrid seismic zone, which extends throughout this whole area, which is where those large earthquakes were in 1811 and 1812. And then we have some along the Appalachian Mountains, as you might expect, and the Blue Ridge Mountains, as those mountains are adjusting to crustal crustal forces. So earthquakes are going on all the time. So let's talk about faults in general just for a minute. So there are three basic types of faults, and we'll see some examples of each of those. First is what's called a normal fault. That's where you've got extension going on, and that is where you have what's called the footwall dropping down in relation to the land surface. And these are very common on passive margins, as you might expect. When ocean basins are pulling apart, you get these normal faults, and you get large sediment-filled basins actually all up and down the southeastern US, particularly well exhibited in North Carolina, that are full of sediments, and these basins were developed as the Atlantic Ocean was opening up. Secondly, we have something called a reverse or a thrust fault. As you can imagine, when you have compression, you have a compression of an area, and if there's a fault and there's movement along that fault, it's going to be causing overriding or thrusting of the hanging wall up on top of the land surface. And these are much more common in active margins, as you might imagine, because of the compression in those kinds of settings. Strike slip faults, those are where there's no vertical offset, but where there is movement across the fault, and you see that as an offset in the location of features on the land surface, as opposed to looking at offset in bedding, as you might in a road cut with a normal or a reverse or thrust fault. And you can find these typically in active margins as well. So I just want to show you a couple examples. So here's a normal fault. Anytime you have two rock units moving against each other, you have some kind of a fault zone. It can be a fault gouge zone where it's very fine grained, and that's what you're looking at here. Or it can be something called a breccia zone, which is what we're looking at right here. You can see there's very large, coarse granules here. You haven't gouged it out to very, very fine grained material. And the other thing that's interesting here is you can see the fault surface right here. And if we orient ourselves 90 degrees to that view, you can see, looking down this surface, that there's been a mine put down along this surface, because quite commonly on these fault surfaces, you get zones where water can percolate, new minerals can be deposited, and a lot of times these will be zones that are enriched in things that you want to mine for, like gold and silver and nickel and things like that. So if we look for what strike slip faults and what they look like in surface expression, we can look in satellites. We're looking here. Here's San Francisco Bay. Here you can see the trace of the San Andreas Fault. And one of the features that shows up are a number of lakes that have formed right along the fault itself, where the fault has created less resistant materials that have eroded out, forming depressions. And the fault crosses across the bay mouth, goes up through Tomales Bay, and then goes out to sea just north here. But you can see that linear feature. And if you ever fly into San Francisco, airport's right up in here, and you land right, and you can look right down along the San Andreas Fault. This is another image of the San Andreas Fault further south in the Central Valley in California. This is an area that's very arid. There's not a lot of plants. The movement of the fault, which is a strike slip fault, remember, so there's no vertical offset, but it creates less resistant material on either side of the fault, which can be weathered out and eroded away, showing the trace of the fault. One of the cool things about fault movement with strike slip faults, that in some areas it moves very slowly and very methodically. In some other areas, it locks up and moves abruptly. But in areas where it's moving rather slowly, you can get interesting features like this creek that was coming down, and then it's offset because of movement along this the relative motion. This side is moving this way, this side is moving that way. Here's the trace of the fault. And if you look at it from a more of an aerial view, you can see that same channel, or another example, I guess, of that same channel, offset across the fault boundary. So there are expressions of active tectonics that you can see in areas that have that don't have a lot of sediment on top of them. Then I want to show a couple other examples of lateral strike slip faulting that happens very abruptly. Here's an example from Central America, where we had a line of trees which moves 8 or 10 feet to the other side here across a strike slip fault during a single event, during one of these large earthquake in Honduras. Here's some plowed fields in the Central Valley in California. And so these fields have been plowed, and there was an event that offset all these plowed ridges. So we can measure how much the fault moved, and we know it happened relatively abruptly, because certainly these would not be preserved if it was a long-term change, because the farmer isn't going to leave his field sitting for years in this way. Then here's a couple examples of reverse faulting. Here, this is in Australia. You can see that there's a large ridge all the way along here. It's casting a shadow because the sun is low. And that's because this side of the fault has been thrust up over this side of the fault. And that created a ridge on top, and those sediments have collapsed. Now, the other thing associated with large earthquakes is that there are strong ground motion effects, and that some of the shaking can actually create some really wild effects. So I really enjoy seeing these railroad tracks that, because of a seismic wave moving through the area, were bent and offset. Here are two examples, one down in South America, again, this one in Australia. And so these strong ground motion effects can be very important and impactful to built infrastructure. And so that's something that we need to start thinking about. How do you build best in areas of high seismic risk? And I'm not going to talk much about that at all tonight, but I'll be happy to talk about it in the question period if someone has a specific question. So one of the really nice things associated with large earthquakes, and these are only formed in earthquakes that have at least a magnitude 6 or above, are something called sand blows. These are small sand volcanoes, basically, which only occur when you've got saturated sands that are no more than 15 or 20 meters deep under the ground. When you have pores that are full of water in sandy deposits, when it gets hit with a shock during an earthquake, you can overpressurize those pores, which will fluidize that mud. And if there's enough overburden from the sediment and soil sitting on top, then that fluidized sand can be pushed up out of the ground and form these little sediment volcanoes. And if you've ever been at the beach standing in the wet sand down by the water and moved your feet back and forth really fast, pushing hard on the sand, and you've sunk down into it, you've experienced liquefaction and this kind of a process. The nice thing about sand blows is we know they're only associated with earthquakes that are Richter magnitude 6 or greater. And they form these nice little volcano holes at the surface. There's one here, there's one here, there's one here, there's one here. And what happens relatively rapidly, because these are right at the surface, is that these little holes fill with organic matter, leaves and twigs and other kinds of organic matter. And once these get buried, that organic matter is preserved. And if you can find these sand blows in the sediment record, then you can date when these relatively large earthquakes occurred. And we'll find out that that's useful in a few minutes. So let's get back to talking a little bit about our local area. This is just the earthquakes since 1900 that have occurred in our local area. You can see there's quite a few of them. That's why the Charleston earthquake doesn't show up, 1886. But there's been a number of earthquakes along the Savannah River. Now, most of these are caused by the filling of the reservoirs, because when you're loading tons and tons of water on top of areas that did not have that kind of overburden before. And so you have some adjustment underneath those reservoirs. There has been one earthquake in Savannah. It was a 4.1 in 1903. So it wasn't a very large earthquake, but we have had a history, if you want to call that a history, here in Savannah. Now, the large earthquake in 1886 that occurred in Charleston, well, it was the Charleston earthquake because that was where most of the development was at the time. Here's Charleston down here. The epicenter of that earthquake was actually up here near Somerville. So as you drive up I-95 and you see the exit sign for Somerville and Ridgeville, you'll know you're near the epicenter for the Charleston earthquake that took place about 140, little under 140 years ago. On this panel on the right, you can see that here's a summary of earthquakes from 74 to 2002, which shows that that area is still an area of activity. And of course, the color again is showing depth, but most of these earthquakes are occurring somewhere between 4 and 12 kilometers beneath the surface. So they're not very deep. So that's telling us that they're on some sort of a buried fault system. So back in 1704, when Charlestown was founded, the city was built on what little highland there was in this peninsula between the Cooper River and the Ashley River. And it was also built on a lot of filled-in marsh. That came back to haunt the city of Charleston in the 1886 earthquake, because one of the features of not being built on solid rock or very well compacted sediments is that if they do fluidize, you get more damage because there's more shaking of your buildings. And if you look at where the damage was located, most of it is located in this early established part of the city that was built on salt marsh extending up in. So we're talking about this area up into here. So what your substrate is very important when you're building for earthquake resilience. So I've got a few pictures here just to show you some of the examples of the damage. This is the old courthouse on Meeting Street. One of the things that occurs in earthquakes is that if you have brick or masonry structures, which is very popular here in the South, those bricks all fall down. So we've got all the facades off of most of the buildings in Charleston were on the ground. They came from up here, and they just collapsed during this earthquake. Wooden structures tend to do better because they're able to withstand and move a little bit when the ground starts to shake. I'm not saying that they won't be damaged, but they're less likely to bury you under tons of brick. Here's another image from East Bay Street, for those of you that are familiar with Charleston. And again, just showing the commercial district. Piles and piles of bricks are a very common feature in the in the photos from this time period, because people were piling up all the bricks that had fallen off all the buildings. And blessedly, we also found sand blows. This is a very large sand blow that occurred in a river valley near Charleston. And again, these are features that allow us to put a time frame on earthquakes of a large magnitude. So, you know, the question we really would like to get at, given the distance that Charleston is away, a little bit less than, you know, 90 kilometers, we would like to know what the recurrence interval of that Charleston earthquake was. So some very smart guys decided that they would go out and look for evidence of sand blows. So they were all over the coastal plain of North Carolina, South Carolina, and Georgia, looking in drainage ditches and along river valleys, any place where they could get a cut face where they were looking for a depression that might have organic matter in it. And when they found those, they excavated the organic matter out, and then they would carbon date that organic matter to get at when that sand blow was created. Now, knowing that you have to have a magnitude 6 earthquake, at least from people's experience with the science of sand blows, they've found that they were finding sand blows that go back to about 6,000 years ago. The thought is you don't find anything older than that because sea level was so much lower before 6,000 years ago that you didn't have saturated soils that would support the creation of sand blows. But they did find a relatively constant recurrence interval of about 400 years between events. So this last earthquake, 1886, a little bit less than 140 years. So we've got some time before the next one. But it's something that we need to keep in mind when we're building structures that need to be resilient to these kinds of things. You know, when I first moved to Savannah, I was coming from the West Coast, so you know I wasn't surprised that we needed earthquake insurance there. But when they wanted to put it on my homeowner's insurance here, I thought, why would I need that? But now I see why. So the effects on Savannah from that earthquake in Charleston, we have some records of what went on during that time. There were seismic waves, both body waves that traveled through the earth and then surface waves that traveled along the surface of the earth that arrived about 45 seconds after the earthquake, and the shaking lasted for about a minute and a half. Luckily, you know, there was a lot of panicking going on, people jumping out of windows to get out of buildings, but no one died. Lots of chimneys came down, a few buildings were destroyed, but it wasn't a big event here in Savannah. The thing that I thought was impressive is that the Tybee Lighthouse wall cracked where it was 6 feet thick, and it shifted the lens at the top of the lighthouse about 1.5 inches in a northeasterly direction, which they used to get an idea of where the seismic shaking had come from. So we did experience effects from this earthquake, but because the sediments here are relatively unconsolidated, you know, we've got a lot of sand and dirt here. We don't have a lot of solid rock. We don't transmit seismic energy very well, and that seismic energy gets sapped up fairly quickly. Now, in Colombia, it was a different matter. You know, that's going inland. It's traveling through a lot more high consistency rock material, and the coastal plain sediments are getting thinner and thinner. And so damage was much worse, even though it's just about the same distance from Charleston as Savannah. Okay, I'd like to switch gears now and talk about tsunamis, or what are called seismic sea waves, which are waves that are created during earthquakes, and we'll talk just in a moment about how that occurs. But these are waves that get created on the ocean surface and which propagate throughout the ocean basins. So these are locally derived phenomena, but which end up being felt around the world. Now, and depending on what the magnitude of the event is, we feel they're catastrophic or not. So how do we create a tsunami? This little diagram here on the upper left kind of shows that. And now this is showing it associated with an earthquake, which is typically associated with subduction, where one plate is being dragged down underneath another plate, which is overriding it. Typically what happens is you get that the two plates get locked together. And so over time, the lower plate drags down part of the upper plate. And then when an earthquake occurs, that's when that energy is released. The overriding plate springs back and creates a upward bulge in the sea surface. And that upward bulge spreads out in both a landward and a seaward direction, creating waves. That's why the first thing that you see from a tsunami is always a trough. You always hear stories about, oh, the water's receding from the shore before the first tsunami wave came in. And that's because the crest of the wave always is led by the first trough of the wave. The reason these features are become very dangerous is because out in the open ocean, these things have very, very long wavelengths. And so they really don't have a lot of amplitude. They're not very high waves, but they move very quickly. In deep ocean water, they may be moving about as fast as a jet plane, and then they slow down, and those waves get piled up as they start to get into shallower and shallower water until we reach these very high magnitude waves that come ashore, and typically there'll be 3 or so in a tsunami train. Now, given that they're so long wavelength where they're created out in the open ocean, this becomes a problem, because how do you find something like that? If you were out on a boat in the middle of the ocean, you wouldn't even notice a wave with a 200-kilometer wavelength passing under you. And so there's a system that's been created called the DART system, which has put out buoys which have pressure transducers at the bottom of the ocean. They have wave measurement sensors at the surface. They have GPS antennas, which give them a highly accurate vertical elevation. And so they can start to determine wavelengths and they know when they need to look, because it's only after large seismic events. Most of these are deployed throughout the Pacific and Indian Ocean, but there are a few in the Atlantic Ocean as well. Now, why are there only a few in the Atlantic Ocean? And it's because although there are reported tsunamis from all the ocean basins, we don't really have a long history or a large history of them occurring in the Atlantic, as we'll see very shortly. The Pacific, of course, we've talked about that, the Pacific Ring of Fire, lots of subduction zones, lots of areas that can generate large earthquakes. And if you remember the 2011 earthquake and tsunami in Japan, that was a good example of the kinds of events that can occur in the Pacific Ocean. We have records that date back quite a long way of tsunamis coming ashore in areas where we have longer written historical records. And unfortunately, because there are some areas where there are not long written records and where we have not had instrumentation in place, there is a poor catalog or history of tsunamis in some parts of the world. So it's hard to talk about and predict what the recurrence interval for these kinds of features might be, other than to go and use geologic kinds of indicators like tsunami deposits. Now, this figure on the left basically shows, the blue is earthquake-derived tsunamis. That's 81% of all of them. 4% is probably earthquake. And so we're talking, 85% of tsunamis are generated by earthquakes, and with the remainder being from either landslides or volcanic eruptions. So the best known areas to generate tsunamis, of course, are all these yellow areas that we've talked about already, the subduction zones, the areas where we have compression, and these areas that have times and dates associated with them, these are areas that have seen major tsunamis. So again, up Japan and the Aleutian Islands. Here, one of the more recent ones on this figure, this is the Banda Aceh tsunami that devastated the region around Malaysia, and down here in Chile in 1960. So there are large magnitude earthquakes. Again, really nothing in the Atlantic section of the US. When we look at areas of the coast that have been impacted by tsunamis over time, we can see that all of the Pacific coast down to Santa Barbara and all of Alaska was affected by a tsunami by the 1964 Prince William Sound earthquake. Hawaii has received tsunamis from Alaska and Chile. You notice the sides of the island that saw the tsunamis correspond to the direction where you find the tsunami sources. Puerto Rico has associated with them, and then some other areas up in Cascadia have been impacted as well. Again, no significant tsunamis associated with the east coast of the US. So let's talk about the Atlantic Basin. We've already talked about there being a very relative small number of tsunamis. Probably the best well-known, well-documented large tsunami occurred in Lisbon in 1755. There's a fault just located offshore of Portugal, and that was had a large earthquake that generated a 15-meter high tsunami, which destroyed several ports, sunk ships in the English Channel, but the impact of that was relatively localized to this part of the Atlantic Basin. The one that most people have heard about is the Grand Banks earthquake and submarine landslide that occurred, which created a tsunami, all of which was only felt up here in Newfoundland. And then there has been discussion about a Canary Islands tsunami threat, which we'll talk about a little bit more in a minute. So we've talked about earthquake generated or seismic tsunamis, but you can also generate a tsunami by large scale failures under the water in the ocean. And in fact, those have been the kinds of features where we have seen tsunamis here on the East Coast. So when you have a large slump failure that goes down, you translate water up and once again create an outgoing and a backgoing tsunami. And there's other features like turbidity currents that can be used to document these features. But again, you've caused a bulge in the water that propagates out. You can have these be very localized features. Here's in Latuya Bay in 1958, this section of hillside basically slid away and created a tsunami that reached over 1,700 feet high, sweeping all the forest off of here and clearing the forest away from this whole area. So localized, they can be very impactful. And this is just a photo from up in Newfoundland in the area associated and impacted by the Grand Banks earthquake as well. So knowing that this is a important process on the East Coast, there was a lot of work done in the 90s into the 2000s trying to map out landslides to see whether there are incipient features or evidence for landslides along the East Coast. There were a number of slope failures, large slope failures that were mapped, although we don't have any evidence that tsunamis were associated with those features. And these are the kinds of things, this is from the West Coast, but this is the kind of thing we're looking for. Areas where you might have large failures of sediment moving down the continental slope. And looking here off of Southern Virginia and North Carolina, you do see there are areas that might look like they are incipient failures. And so there is the potential that we could see tsunamis. The tsunamis that we have seen along the East Coast so far have been relatively small, all less than a couple of meters at the end of the day. So I want to end with this, which is the hysteria around the Canary Islands. So the Canary Islands are located here off of the northwest coast of Africa. And a couple of decades ago now, there were some UK scientists who said, if La Palma, which is one of these Canary Islands, they're volcanic islands, very steep-sided, and if the side of one of these volcanoes just slumped away during an earthquake or an eruption, and the deposit slumped in exactly the right direction, that we think that you could generate waves that might be 130 to 160 feet high coming across in 8 hours to devastate the east coast of the US. So every time La Palma volcano erupts, like this is from October 11, 2021, right? La Palma volcano erupts today, possible tsunami and earthquake. So every time there's eruptions in the Canary Islands, the less reliable media starts hyping this large tsunamis that might strike the east coast of the US. And the more careful work is down here, done in 2015, looking at the more reasonable sized deposits, but the more reasonable failure directions. And if you look at the maximum magnitudes that you might find, yes, you might see tsunamis up to 4 meters, maybe up to 5 or 6, if you have the whole side of one of these volcanoes go down. But if you have a more reasonable sized deposit that are more similar to what they've been able to map on the flanks of these volcanoes in the Canary Islands, more like 80 cubic kilometers of material instead of 450, then the tsunamis never get over a meter or 2, which are not really a major threat to people or infrastructure by and large. So with that, I'd like to end and ask if there are any questions for me. And Dan, I think you're going to moderate.
That is the plan. Yes, thanks, Dr. Alexander. All right, we'll usually let a few minutes or two for folks to type any questions into the chat.
Oh, sure.
They don't have to turn on their logins. I had a few things that I want to start with. It's worth noting that you signed up for this talk long in advance of the now ongoing La Palma eruption, correct? You signed up for this talk probably in December of last year, so it's just a coincidence that it's ongoing right now.
But it's really, really impressive.
Yeah. It's especially impressive when a geologist times things. Okay, let's see. So one thing that I noted was I was curious whether especially given the rarity of seismic events around here in Georgia, do you know, this is maybe outside of your expertise, but are there building codes? Like, is seismicity considered at all in new constructions in this area, like it is in the West Coast?
I don't know whether it's fully incorporated, but I know that there are not full earthquake standards for new building construction.
Yeah, so there's no like, it must withstand a certain magnitude type consideration.
Right. There's a lot more attention paid to making sure the roof will stay on in a hurricane and your windows won't blow out than
Right.
whether your house is going to fall down in an earthquake.
Great. Okay. That's what I expected. Okay, let's see some other things. So if I remember correctly, the like Charleston earthquake is an intraplate earthquake, right? It's relatively rare for earthquakes to happen in places like that, right?
They're relatively rare, but they do happen. Yes. One of the problems that we have all along the East Coast is that there undoubtedly are beaucoup of fault systems. We just can't see any of them, and their expression of movement doesn't show up at the surface. So we really don't. And so for long recurrence interval earthquakes, people who have been keeping records of earthquakes, I guess Europeans, I'll say, have not been around long enough for some of the long recurrence interval earthquakes to have been recorded. I mean, on the West Coast, there have been some, long-term records using, native knowledge of the systems, but I'm not aware of any of that from Georgia or the Southeast.
Oh, okay. Yeah, and that was my related question, was that for these really rare earthquakes, it must be impossibly difficult to estimate some kind of recurrence interval for them, right? Even if there had been excellent monitoring for hundreds of years, right?
Right. Now that being said, there were native peoples in these areas, and at least in the Pacific Northwest, there were what do I want to call it? Tribal knowledge, incorporated history that speaks of these kinds of events. They're not recorded as we might record them as scientists, but they still contain useful knowledge that can be incorporated into a longer term understanding.
Oh, interesting. There's a question in the chat here. It says, hello, Clark. Do you know if earthquake emergency planning is part of local planning? And for instance, like, have you ever been consulted on it by SEMA, or if there are plans, like, do you know of them?
I don't know whether there are as fully fleshed out plans for earthquake response as there are for other kinds of disasters. I've never been called on. Frankly, my credentials for talking about earthquakes is that I grew up on the West Coast and got my undergraduate geology degree in an active tectonic setting. So I'm not an expert by any means.
Yeah, it's an interesting point though, because I lived in Southern California for a while too, and a lot of the earthquake response is really around like managing fires and managing, like, similar to what you'd manage for a hurricane, where you imagine like large scale damage to multiple buildings and multiple traumas and stuff like that. So I imagine in a lot of ways the plans for those types of things would be applicable.
Yeah, I think that's very true. A lot of the resources are the same.
Yeah. And have you done, do you know from any of your research in comparison to like other countries? Like, I've heard in the past that the US is considered like relatively underprepared for earthquakes compared to, clearly Japan is like one of very well prepared. But like even to other countries sort of in Central America and Chile and countries that are located on the west coast of South America. Is that true in your experience?
I really don't know.
Yeah. I just think of like earthquake warning systems and things like that. So
yeah, the West Coast is just now really taking that on, as a civic responsibility. Getting there's a whole new generation of tsunami modeling and tsunami potential mapping going on all up and down the west coast of the U.S. And I've seen that when I've been at meetings, that there are very detailed plans being developed. There are a lot of plans for response to earthquake, but there really had not been good planning for responding to tsunamis.
Yeah, interesting. I imagine that texting and basically alert messages and like that would be used even if there was sort of any kind of suspicion, right?
Right. There's that, and the other thing that has taken place in a number on the West Coast as well is the identification of safe areas to go. Here's we have hurricane evacuation routes. They have tsunami safe zones, which are at a elevation high enough that it should be above the predicted tsunami for the earthquake that they expect in the area.
Interesting. It seems like the final question is here. So since you're bringing some personal experience into the discussion, have you ever been in an earthquake on yourself? And if so, what was it like?
Yeah, I've been in a number of earthquakes. I grew up in Los Angeles, so let's see, there was a large earthquake in '79. I remember I was in my little twin bed, and I thought my mom was trying to get me up because she was shaking the bed so hard, but it was just the earthquake shaking the bed. So
oh, wow.
it's I mean the only it can be it happens fairly quickly. That's the thing. Give me a earthquake any day, right? It starts, it's over within a couple of minutes, and your future is before you, whatever that's going to be. There are a lot of other much slower moving disasters that you have to watch for weeks to figure out what's going to happen. Flooding, hurricanes. I'd rather my disasters be quick.
Yeah, interesting. Yeah, I was in a minor earthquake in Boston when I was in graduate school, and everyone thought that they had just gotten a little nauseous. Like it was just enough vibration to make everyone think that they were like blurry or whatever from looking at their computer screens. And one of the geologists came into the room and was, "Did everyone feel that?" Probably
Yep.
magnitude 3 or something.
Yeah, the USGS has a website where you can go and report, did you feel it? And that's how they crowdsource information on how far away seismic waves traveled. And every once in a while, people will feel earthquakes. There was the earthquake up in Virginia in 2017, I believe.
Mm-hmm.
Yeah, I think. But there were people down here in Georgia who said they felt that.
Yeah, interesting. Great. Yeah. Oh, I read a New Yorker article about there was a geology conference going on during in Japan during the earthquake that caused the Fukushima reactor meltdown.
Mm-hmm.
And the New Yorker did an article about it called, it's basically about earthquakes devastating the Pacific Northwest, but they have a whole recounting of that earthquake through the eyes of all the geologists who were there at the conference. And they go into those reports about, because the magnitude is related to how long the shaking lasts. And so, in the first 10, 20 seconds, everyone was sort of chuckling. And then after about a minute and a half, everyone's like, "Oh, we need to get out of here. This is a big one."
Yeah. I'm sure that makes interesting reading.
Cool. Thanks, Dr. Alexander. Is there a final slide that shows the upcoming talks? Yes, great. So just under a month from now, Dr. Jay Brandis will give a talk about ocean plastics, and we'll look forward to see you then on November 9th. Thanks again, everyone.
Thank you. I appreciated the opportunity.